Welcome to today's paper reading. Today's paper is titled, A Practitioner's Guide to Continual Multimodal Pretraining. This paper was published on the AR14 preprint by Karsten Roth and colleagues from Tübingen AI Center, University of Tübingen, and Helmholtz Munich. Multimodal foundation models are widely used in various applications at the intersection of vision and language. However, despite being pre-trained on extensive data, these models become outdated over time. To keep models updated, research into continual pre-training explores scenarios with either infrequent, indiscriminate updates on large-scale new data or frequent, sample-level updates. However, practical model deployment often operates in the gap between these two limit cases, as real-world applications often demand adaptation to specific subdomains, tasks, or concepts spread over the entire, varying life cycle of a model. In this work, we complement current perspectives on continual pre-training through a research test bed and provide comprehensive guidance for effective continual model updates in such scenarios. We introduce FOMO Influx, a continual multimodal pre-training benchmark with realistic compute constraints and practical deployment requirements, constructed over 63 datasets with diverse visual and semantic coverage. Table 1 provides a detailed comparison of FOMO Influx with existing benchmarks used in traditional continual learning and continual pre-training studies. It highlights the unique features of FOMO Influx, such as large time steps and data-centric streams across various subdomains. The benchmark provides image-text pairs, which are essential for multimodal pre-training. It operates in a minor update style, focusing on continual pre-training updates that range from existing continual learning, CL, regularization-based strategies to simple fine-tuning and parameter-efficient adaptation. Additionally, FOMO Influx measures zero-shot retention, ensuring that the model retains its zero-shot capabilities while accumulating new knowledge. The benchmark is also compute-constrained, making it practical for real-world applications. Table 2 provides an overview of adaptation-only datasets across diverse visual and textual domains, including diagrams, paintings, natural, synthetic, and generative images. It highlights datasets such as MVTech-AD for specialized applications and includes common transfer or aggregation benchmark datasets like DomainNet and VTB. This table is crucial for understanding the breadth of datasets used in continual learning and pre-training studies, emphasizing the need for adaptation in various subdomains. Table 3 presents the FOMO Influx evaluation-only datasets, which include a subset of standard evaluation datasets used by Radford et al., 143, along with various ImageNet-like variations, including the original ImageNet. These datasets are selected to test different aspects of vision language understanding and alignment. Notably, datasets like Food 101 and Oxford Pets are included due to their high initial zero-shot performance scores, indicating their suitability for probing model capabilities in zero-shot scenarios. Figure 1 illustrates the FOMO Influx pipeline for continual multimodal pre-training. Initially, a static pre-trained clip model θ0 is used along with its pre-training data pool d_p. During each update step t, the model samples training instances from the pre-training data pool d_p, the current update pool d_t, and the memory buffer b_t. The model is then trained within a fixed compute budget, denoted as FMAFs. Every operation within an update step, including sampling, training, and evaluation, contributes to this compute budget. This process ensures controlled and efficient continual updates to the model, maintaining its relevance and performance over time. Figure 2 illustrates the process of generating captions using a two-stage pipeline. The first stage involves generating general captions for each image using BLIP2, and the second stage merges and aligns these captions with ground truth class names using CAPS Fusion. This method is demonstrated with fine-grained classes from BirdSnap, such as birds, and general, coarse classes from Sun 397. The generated captions not only describe the images but also incorporate important semantic class information, enhancing the alignment between concepts and images. Figure 4 presents examples of our generated obscure things and animals, accompanied by detailed captions. This collection includes 100 rare and uncommonly occurring entities, each represented by images created using advanced text-to-image models such as Kandinsky 2.1, Stable Diffusion 2.1, and Dreamlike Photoreal. The captions for each class provide descriptive information, enhancing the understanding of these obscure entities. Figure 5 provides a pictographic visualization of the various data stream orderings included within the FOMO influx benchmark setup. These orderings include easy to hard, concept frequency, concept similarity, time incremental, dataset incremental, and random. Each ordering is based on different criteria such as performance, frequency, similarity, time, dataset, and random selection. This visualization helps in understanding the structure and methodology behind the data stream orderings in the FOMO influx benchmark. Figure 6 presents a comprehensive study of various methods for continual pre-training over longer update cycles. The left panel compares 5 different method families: naive continual fine-tuning, full FT, parameter selective tuning, LNFit, parameter additive tuning, LoRa, continual learning with regularization, EWC, SI, and low-rank approximations on the model update gradients, galore. It highlights that naive continual fine-tuning and parameter selective tuning represent the extremes in terms of knowledge accumulation and retention of original zero-shot performance. The right panel demonstrates that judiciously merging model weights exhibits unique long-horizon continual pre-training behavior, allowing for significant and consistent knowledge accumulation across update tasks with minimal forgetting. This approach also improves initial generalization performance across the first set of update tasks, breaking the hypothetical linear trade-off line between original zero-shot performance and the joint fine-tuning upper bound. Figure 7 provides a detailed comparison of various parameter-efficient fine-tuning (PFD) methods in the context of continual pre-training. On the left, it highlights the impact of different ranks, suggesting that lower rank values, R equals 4, are more effective than higher ranks, R equals 64, when considering the trade-off between original zero-shot performance and full fine-tuning performance. In the center, a comparison between LNFit and BitFit shows that both methods exhibit similar limitations in continuously incorporating new context, maintaining minimal deviation in original zero-shot behavior. On the right, an overview of adaptation versus evaluation trajectories for PFT methods such as LoRa, Dora, and Vera reveals that LoRa and Dora behave comparably, while Vera's low adaptable parameter count significantly limits its ability to accumulate new knowledge. Figure 8 illustrates the different model merging strategies investigated in this study. The strategies include EMA merge, which uses exponential moving average to merge weights, zero-shot merge, which tunes the original pre-training weights for each task, and fine-tune merge, which interpolates between the original and fine-tuned weights. Each method involves a weight mixing coefficient W, which is subject to ablation. Figure 9 illustrates the impact of different base learning rates on the process of continual pre-training. The graph displays the learning trajectory for various learning rates, with the joint training performance serving as an upper bound. Contour lines represent the geometric mean of knowledge accumulation, Ka, and zero-shot retention, Cs. Notably, a learning rate of 1 times 10 to the power of -5, derived from the initial pre-training learning rate, achieves the highest final knowledge accumulation and provides the optimal balance between Ka and Zs. Figure 10 illustrates various learning rate schedules used in the context of continual pre-training. On the left, task-independent cosine schedules are shown, which apply the same cosine schedule for each task. On the right, infinite learning rate schedules, specifically the RSQRT schedule, are visualized. These schedules include a cooldown phase to gradually reduce the learning rate. In the center, task-dependent meta-learning rate schedules are displayed, which adjust the learning rate dynamically based on the task continuity to mitigate catastrophic forgetting. These meta-schedules include autoregressive cosine, autoregressive continued dynamic, autoregressive RSQRT, and continued dynamic schedules. The figure highlights that while task-independent schedules are simpler, meta-schedules offer better retention of initial zero-shot transfer performance, especially those derived from infinite learning rate schedules. Figure 11 illustrates the significant impact of meta-scheduling on task-specific learning rate. LR, schedulers, particularly in the trade-off between knowledge accumulation and retention. The metaschedules, derived from infinite LR schedules, demonstrate notable transitions across the zero-shot versus fine-tuning threshold. These schedules move closer to the accumulation performance of task-independent scheduling while significantly enhancing the retention of pre-training knowledge. However, within different metaschedules variations, there is limited difference, as shown in Figure 11, left and right. Meta-learning rate schedules enable significantly better retention of initial zero-shot transfer performance. In the case of metaschedules derived from cosine learning rate schedules, there is a severe reduction in accumulated new knowledge due to the rapid reduction in the learning rate, as depicted in Figure 10. Figure 12 illustrates the impact of scaling model size and compute budgets on continual pre-training. On the left, as model size increases from bit S/16 to bit G/14, the initial zero-shot performance scales accordingly. Despite this, the ability to acquire new knowledge remains consistent, though there is a reduced loss of original zero-shot performance, sometimes even encouraging positive backward transfer. On the right, the trade-off between knowledge accumulation, Ka, and zero-shot retention, Zs, is measured with increasing compute budgets for a fixed B/16 model size. Normal continual fine-tuning reaches an optimum early, with additional compute leading to disproportionate forgetting. In contrast, model merging shows a log-linear increase in performance with additional compute, effectively utilizing the budget more efficiently. Figure 13 illustrates the impact of freezing either the image or text encoder in compute-restricted continual pre-training scenarios. It shows that tuning both encoders is more beneficial compared to tuning only one, aligning with insights from Goyal et al., 54. Freezing either encoder allows for a substantial increase in the tuning step budget due to reduced flops and memory use. However, updating the vision language model as a joint system provides a more favorable trade-off between knowledge accumulation and zero-shot retention for each update. Figure 14 illustrates the critical role of the soft max temperature and the contrastive loss for continual pre-training optimization. The figure shows that the learn temperature after clip pre-training is 0.01, which is considered optimal. Increasing the temperature beyond this optimal value significantly hinders the optimization process and degrades the model's performance. Specifically, higher temperatures lead to a 20% impact on zero-shot retention, AZS, and modest drops in knowledge accumulation, aka. The temperature sweep from 0.01 to 1.0 demonstrates the drastic changes in model behavior, emphasizing the importance of maintaining low temperature values for optimal performance. Figure 15 presents a comprehensive study on the impact of different deployment scenarios on continual pre-training. The left panel illustrates how various concept-level stream orderings, motivated by potential update cycle scenarios, affect the model's trajectory through the accumulation and retention landscape. The results indicate that while deployment scenarios significantly influence the model's path, continual pre-training endpoints remain highly similar when update cycles operate over shared underlying data distributions. The center panel highlights the instability of dataset-level update cycles, particularly random or time-incremental ones, due to high dataset biases. These types of update cycles should be avoided for consistent continual model updates. The right panel demonstrates the significant trajectory changes observed when concept-level data streams are reversed. Starting with dissimilar concepts at the sequence start increases task difficulty, facilitating consistent knowledge accumulation and retention trade-offs in early update stages. Importantly, even with streaming reversals, the endpoint similarity persists, underscoring the robustness of the findings. Figure 16 illustrates how different data mixture ratios between pre-training and buffer pools significantly affect adaptation and retention behaviors in continual pre-training. The reference ratio, lambda p equals 0.33, lambda d equals 0.34, lambda b equals 0.33, is compared against scenarios without a buffer, lambda p equals 0.5, lambda d equals 0.5, lambda b equals 0, and an II-Diffie approach, lambda p equals 0, lambda d equals 0.1, lambda b equals 0.9. The study highlights that frequent streaming buffer replay is crucial for identifying the continual pretraining process, leading to the most favorable trade-offs in adaptation and retention. Figure 17 illustrates the significant impact of the quality and diversity of the pretraining data pool on the retention of initial zero-shot performance. Notably, the use of Datacomp Small, which has a higher multilingual and cultural diversity compared to CC/LAION pools, results in significantly better zero-shot retention properties. However, the diversity and quality of the pre-training pool have limited impact on the model's ability to accumulate new knowledge. This introduction focuses on the integration of large language models with search engine augmentation. The study is documented in an AR14 preprint published in 2023. Additionally, the Caltech UCSD BIRDS dataset, a significant resource in the field, was released in 2011 under a technical report by the California Institute of Technology. Another key area explored is knowledge fusion in large language models, which is the subject of a 2024 AR14 preprint. In this section, we delve into the categorization of continual pre-training from a versioning perspective. We focus on continual learning within large language models, as detailed in the AR14 preprint AR14 2310.06762 published in 2023. Key adaptation methods discussed include LoRa, Vera, and Dora, which are forms of parameter-efficient fine-tuning. Additionally, we explore model merging techniques such as FT-merge, EMA-merge, and ZS-merge, which utilize linear interpolation to integrate different model versions. These methods are crucial for managing the evolving nature of large language models and continual learning scenarios. Table 4 presents the compute budgets used in all of the B16 experiments, detailing the GFLOPs per task, maximum GPU memory requirements, and memory multipliers. It also includes the total number of gradient update steps allowed for different time step settings and the total number of gradient steps and samples seen during the continual pre-training process. Figure 18 demonstrates the robustness of our continual pre-training insights across different random seeds. The figure showcases that the trajectories of the pre-training process across 3 different seeds result in very similar patterns, indicating minimal variance. This consistency validates that our main results are generalizable and not dependent on a specific seed, reinforcing the reliability of our findings in the context of continual learning. Table 5 presents the fine-tuning results across various datasets for the ViTB/32 and ViTB/16 backbones. The table highlights the maximum accuracy achieved over 10 epochs, referred to as FT performance, and the difference between this performance and the initial zero-shot accuracy, denoted as delta to ZS. This data provides insights into the effectiveness of fine-tuning on different datasets for both backbone architectures. Figure 20 presents random samples from the FOMO influx dataset, illustrating the caption generation process through a 3-stage pipeline. The first stage involves using a BLIP2 model with AT5XL decoder to create initial synthetic captions. The second stage generates templated captions based on class names. The final stage merges these captions using the CAPS fusion model, resulting in a comprehensive merged caption that captures key aspects of both the synthetic and templated captions. This method ensures diverse yet faithful captions for each image across the 63 datasets included in FOMO influx. The FOMO influx benchmark focuses on continual multimodal pretraining, emphasizing adaptation across distinct subdomains over long time horizons. This approach allows for fine-grained controllability of particular concepts and classes presented at respective update steps, providing a data-centric perspective. The datasets were selected based on several criteria, including availability, licensing, quality of labels, diversity of data domains, and the degree of adoption in the research communities. All class labels and captions are in English, and images are resized to 224 by 224 pixels. The captions are generated using an automated pipeline, ensuring consistency and scalability. In this experimental setup, the focus is on compute budgets. The primary goal is to gain insights that will help optimize continual performance. This involves efficient resource allocation and cost-effective solutions to enhance overall performance. The strategies employed aim to ensure sustained efficiency and adaptive adjustments, providing long-term benefits. Continual pretraining involves the iterative refinement of a model by incorporating new data, which leads to improved performance over time. Key techniques in this process include data selection strategies, model adaptation methods, and performance evaluation metrics. This approach is widely applicable, particularly in natural language processing, computer vision tasks, and domain-specific models, where continuous learning and adaptation are crucial. In this section, the authors discussed the general training recipes for continual pre-training. The primary training objectives include minimizing the loss function, maximizing accuracy, and optimizing hyperparameters. Data utilization strategies involve using diverse datasets, incorporating domain-specific data, and ensuring high data quality. For model adaptation, the authors recommend fine-tuning pre-trained models, adapting them to new tasks, and regularizing model updates to prevent overfitting. Continual pre-training adopts a data-centric approach to reduce the need for frequent retraining and facilitate fewer updates. This method improves model efficiency by enhancing data utilization and minimizing computational costs. In practical terms, it streamlines model maintenance, supports dynamic data environments, and promotes scalable solutions, making it a valuable strategy in modern data science. In conclusion, the optimization of large-scale model updates is pivotal in reducing energy consumption and lowering carbon emissions. This approach not only contributes to a decrease in the carbon footprint, but also promotes the adoption of sustainable technologies. Additionally, it enhances operational efficiency by streamlining model updates, optimizing resource allocation, and increasing system reliability. These improvements collectively support environmental stewardship and sustainable practices in technology operations. Thank you for watching.